Being able to control something in the real world from within a piece of software running on a computer or microcontroller is the very heart of many electronics projects. Numerous brands of microchips are designed for just that task, conveniently equipped with USB, breakout boards, and all sorts of extras. The first one that I got my hands on is the IO-Warrior40, manufactured by a company called Code Mercenaries. At the time, I had no particular project in mind and purchased it pretty much at random. Now that I learned a few things about it, I decided to document my experience with this product. The device offers 32 GPIO pins and a software-based I2C interface. According to the datasheet, you can also drive some sort of LED matrix with it, but I never looked into that. For this video, I will focus on the GPIO functionality only. The board is powered and controlled over USB, offering multiple APIs. I went with C++, and as far as I can tell, the tutorials and demo applications are practical and well explained. Furthermore, if you get the starter kit, the chip comes with all required external components, a PCB, and soldering instructions. In comparison with other devices like the Arduino microcontroller, the implementation of the pins is somewhat unconventional. Usually a device wants you to declare the purpose of a pin at startup explicitly. This one, however, doesn't differentiate between input and output. Well, let's ignore that for a minute and just look at what's going on. In the code, you have access to a register of 32 bits divided into 4 bytes, each representing a port. Some ports can provide special functionality, but with regard to GPIO, they're all the same. You can see the bit and port IDs on the PCB. If you set a bit to 0, it will drive the corresponding pin low. What that means is that the circuitry for that pin is switched into a mode of operation which looks something like this. Not exactly like this, but close enough. You get a low resistance connection to ground, also called open drain, because it will try to drain whatever current is available. If you set a bit to 1, the circuitry will switch to this, a high resistance connection to 5 volts. With this in mind, you can connect 2 types of output. If your external component requires an outgoing current to be active, you connect it to ground. A bit set to 1 in the code will now activate the output. If your component requires an inbound current, you connect it to 5 volts and set the bit to 0 to activate. You have to be careful with the second setup because a sufficient resistance of the path must be provided by the component itself. Since a pin can only take about 15 milliamps, you should throw in at least 200 ohm of resistance. So where's the input? Like I said, the board has no concept of input or output, but what it does have is a voltage probe at each pin. In other words, it can read the voltage between that pin and ground. When the voltage crosses a certain threshold, let's say 2.5 volts, you can receive that event in the code. So the trick is to pull the pin voltage high or low by manipulating both the internal pin status as well as the external voltage. The table illustrates the 4 possible combinations. If the pin is set to 0 and connected to ground, you're going to read low in the code. If the pin is set to 1 and connected to 5 volts, you're going to read high. If the pin is set to 0 and connected to 5 volts over a resistor, you've created a voltage divider, and the result can be either low or high depending on the value of the resistor and many other things. Obviously not a reliable strategy. Lastly, if the pin is set to 1 and connected to ground, you're going to read low because most of the voltage drop is going to occur at the internal resistor. The second line illustrates exactly what we're looking for. If you want to use a pin as input, you simply set the bit to 1 and connect it to either ground or 5 volts. In the code, you can then read the corresponding value. The original idea was to connect some LEDs and resistors to a bunch of pins. Unfortunately, most of my spare parts are unlabeled in a big box of random crap, so instead I decided to just have the chip talk to itself. To do this, I soldered this 8-pin header strip to the first port and connected the first 4 pins to the remaining ones. Since I'm not exactly a console warrior, I also made this custom UI to control and read the pin status. The first row represents the status that is set. The second row shows the current value that is read at the pin. The third port is connected to these 8 LEDs which came with the starter kit. They're a good example to demonstrate the open drain type of output. As long as the pin is set to 1, no current flows and the LEDs stay off. If it is set to 0, the pin is grounded and current flows from 5 volts through the LED into the chip and into ground. Moving over to port 0, I can now decide which pins I want to use as input. I check the boxes I want, and the second row immediately displays what value it's reading. If I play around with the output pins, their value is propagated over to the inputs. If you're wondering about delay and frequency of the API functions, as far as I can tell, the application runs steadily at about 900 frames per second, performing one 32-bit write and non-blocking read in every loop. That being said, the actual bandwidth in terms of symbols per second is probably lower because a pin voltage change can be missed if it happens too fast. That's about it. I hope that in the next video I'll be able to do something slightly more useful. Have a good one. Catch you later.